Hello everyone. We are happy to present today Anna Tokareva, who is in Hangzhou Institute for Advanced Studies in China. And I had the privilege to work with her in Imperial College London. So I'm happy to introduce her today. So she will talk about a recent work that intrigued us, and we wanted to hear more details. Non-singular black holes in non-local gravity. Please.
Hello, everyone. I'm happy to present my recent work on the seminar. Please feel free to ask questions and ask me to provide more details if something is not clear. So this talk is about life of the four-dimensional generic action for gravity, which can be understood as quantum effective action, reproducing all loop-resummed amplitudes as three-level amplitudes extracted from this action. And I will consider what will be happening in such a theory in a black hole background. So why we assume such a theory? Actually, if we want to restrict if we want to try to formulate some field theory description of general non-perturbative gravity, then this is the only form which can be written, which affects graviton propagator. The next terms are like Riemann cube and other terms will be affecting only graviton vertices, and we can also assume that they're more suppressed compared to the leading two-point function of gravitons. So for this reason, I will mainly will be studying the properties of this section, but also I will give some comments on what can be the effect of cubic terms and so on. So this section is something which is given by an attempt of field theoretical description of gravity without the framework of string theory, but with the assumption that it flows to some ultraviolet fixed point, which is asymptotically safe. This framework leads to given proper definition of these form factors, gravity form factors. We can achieve that, for example, graviton scattering amplitudes will be finite, will be tending to some finite values, and they will also have unitarity properties. Though we expect this kind of field theoretic description of gravity to be non-local. So I will be talking about initially some gravity Lagrangian described as a four-dimensional field theory, but I will allow certain amount of non-locality, which is emergent in the UV only, not in the IR. So these functions will start from at small momenta. This action will lead to normal general relativity action. Here is the brief summary of approaches to non-perturbative gravity. We can write this action, which will be determining the graviton propagator. All other contributions can be reduced to the same action, in fact. This is a result of tremendous computations that even if we write more terms, then their effect on graviton propagator will be still, can be formulated in terms of these three form factors, particularly in 4 dimensions, one of these terms can be further eliminated because of Gauss-Bonnet combination, in fact, will be an interaction, not a contribution to propagator. So the purpose of my work was to relate to make a link between properties of non-local graviton propagator and properties of black hole singularity. It's not obvious that this link can be built, but I will show how it can be done. So let me first mention consistency requirements to this section to make it describing something reasonable, like GR in the low energies and some asymptotically safe theory at higher energies. at infinite energies. Yeah, let me also mention that in principle, this kind of theory cannot exist, and this is not yet clear. That there are some claims that one can build such theories, such class of theories, but of course, at some point we can find some contradiction on the way. So at this moment, we are discussing this Lagrangian in the sense that we are probing it in different ways. Also on top of non-trivial backgrounds, and looking at what's the result for how it changes the physics of black holes in this particular work. So the consistency requirements so far, all of the basic requirements will contain that we don't allow ghosts. So all these form factors should sum up such that graviton propagator is still ghost-free and it doesn't have any complex poles in addition to ghosts on top of flat space. It should reproduce GR in the low energy limit, so it means like all this mess is just a correction in low energy limit. And also there are no 1/box operators because this will lead to some infrared non-locality, which we don't allow. Another requirement is unitary scattering amplitudes, which in particular requires that it should be they should be at least finite at high energies. No causality violation means that we don't allow complex poles in propagator and amplitudes. This also puts certain constraints on form factors. So these three form factors are known functions. Is there any chance to compute them? There are methods which allow to compute at least some pieces of action, of effective action. In low energy expansion, the Lagrangian has a very limited number of terms after field redefinitions, and in principle, perturbative quantum gravity, EFT of gravity, can be brought also to the same form as here, doing field redefinitions back and putting everything, putting all the interactions to the contributions to non-perturbative propagator. Another approach, which is directly related to action written in this form, is a symptotic safety program. Nowadays, it's based on functional renormalization group methods, which is like a non-perturbative method of computing directly RG running of quantum effective action of gravity. And this works if one can find the flow to ultraviolet fixed point, which was claimed to be found, particularly in the work of Fechler, Lithium, Pavlovsky, and Richard. There is an example of ultraviolet fixed point in gravity, which after this computation, the gravity Lagrangian, in principle, can be, all these form factors corresponding to this fixed point can be explicitly found, at least along at least for real momentum. Another method which can so far was not applied to graviton scattering amplitudes, but in principle it can also give some constraints on form factors. It's related to reconstruction of graviton scattering amplitudes from unitarity and anelasticity, and probably overlap of these two methods can give a lot of interesting information, but this is kind of something which we are working on. Another approach is to start from tree-level Lagrangian, which already has non-locality with these form factors. It is known as analytic infinite derivative gravity, which is renormalizable by power counting. And loop corrections to this Lagrangian, as we believe after rigorous computation, they will still lead to the same form of non-perturbative effective action. So this Lagrangian appears in many contexts where people try to describe gravity in terms of field theory, actually. Not only as effective field theory, but also beyond cutoff scale, beyond Planck scale. So what happens on Schwarzschild black hole background? The simplest thing, at least the very solution of singular Schwarzschild background, quite complicated question, whether it goes through equations of motion of such a non-local action. And a wise way to start this computation is to assume that form factors can be expanded in Taylor series, and this is like just a 3-level Lagrangian, mostly referring to the proposal of analytic infinite derivative gravity. If form factors can be Taylor expanded, then it's possible to derive equations of motion for this Lagrangian as a whole. They take the whole page, in fact, but the trace energy, but the trace of Einstein equation have these 2 lines, and in principle, it has a finite size, and one can try to substitute Schwarzschild metric to this kind of equation term by term, and then examine whether a Schwarzschild static black hole solution is a solution at all in this theory, whether these modifications still allow for having this solution. And let me also mention that if we want, as another property of this section, if we want the absence of scalar degree of freedom, that there are only 2 gravitons, 2 polarizations of graviton as degrees of freedom here, then we must put a condition that F4 form factor must be -3 F1. And another condition forbidding having ghosts is that, well, these 2 are already linearly dependent, but the form factor F4 must be of the form related to exponent of entire function of the Lambertian operator. Entire function is a function without poles, but in this case, a graviton propagator is expressed as a function which has only 1 pole, that's 0, at 0 momentum, but no other roots, zeros or poles. So this condition is very important, that it represents no ghost requirement for the whole. It should be set for the whole non-perturbative fraction. So if the theory is good, it must satisfy this condition. Then what happens with the static black hole solution? So this is,
Anna?
yeah.
So I have a quick question, but before that, do you prefer questions to be asked during the talk or at the end?
Yeah, I think it's better if you ask during the talk, because it will prevent me from going to too many technical details.
Okay. So just a quick question, I kind of got lost. FW. So here you had defined F1, F2, F4, and what was the FW?
Sorry, FW is F4 actually. It's
okay. Now, yeah, it makes sense.
Yeah.
This condition F4 equals to -3 F1 seems to be related in some way to, I mean, there was a way to write a quadratic action that has no scalar cost. So, but that was normally exactly the W squared action, right? So it has other cost, but not the scalar one. I'm a bit confused now how it is related. So in order to show it, do you use any Gauss-Bonnet identity or something? The absence of the scalar cost. To me,
actually, we used ADM decomposition of all this. So we did quadratic perturbation of this Lagrangian. And what helps to see, obviously, that no scalar means that this condition should be satisfied, to me, is ADM decomposition and explicit writing of what are degrees of freedom. There is only one option if you want to forbid scalars. It's the only one possibility. If, of course, I don't allow having F1, F2 having some poles, like 1 over box or 1 over box minus m squared. If I forbid this, then that's the only option. The only option to avoid scalar and settle my two graviton polarizations as the only degrees of freedom.
This might be a slightly different situation, but in the standard quadratic gravity, the absence of the scalar cost was somehow related to Weil symmetry.
But you don't have R-turn. Here it's essential that we have R-turn. Probably
but in the quadratic part, Weil symmetry, if it's satisfied, then adding the R term basically gives you a massive spin 2 and the massless spin 2, but not a scalar cost. It's important that the quadratic part is actually while symmetric. I don't know when here it seems different story, but somehow gave me this impression. Also, this -3, I mean, it is not related, but somehow reminded also because the W squared action in some other language can be written as r mu nu minus 1/3 r squared or something like this. So again, the relative factor is -3, but here it's actually between W squared and R squared, so it's a different situation.
That also might be somewhat different situation because the theory is not a local, it doesn't have ghosts, in fact.
Yeah.
And in order to find the conditions which forbid ghosts, they seem to be quite unique. So that's like a settled requirement in this.
The statement currently is that F4 is related to F1 and is given in this form, right? That you wrote. So the only freedom you are left with is F2.
F2 actually doesn't contribute to the propagator in 4 dimensions. I keep it in fact for at least Gauss-Bonnet combination with the same form factors. It doesn't contribute to propagator, but it's very nice to have a control on how interactions contribute to the procedures which I will be doing further. For this reason, I keep this term because it's the simplest one which I can study. Then the idea is very simple. Just take Schwarzschild metric and substitute to these complicated equations of motion term by term, but there is a problem, in fact. Not only technical problem, but the point is that if one has these terms where these terms proportional to squares of Riemann and Ricci tensors and curvature scalar, in principle, normally black hole is represented, Schwarzschild black hole is represented as a space without one single point. So normally equations of motion lead to r and r min equal to 0 everywhere except one point r, which is the center of the black hole. But when we are having theory with infinite number of derivatives, it's a good question whether we can at all simply exclude the one point out of our consideration, because we need all the functions on which these form factors are acting. We want these functions to be infinitely like smooth up to infinite order of derivatives, and that might not work with. That's a concern of directly saying that nothing new happens. If we don't exclude one point, then one point from the consideration, then it means that Ricci scalar and Ricci tensor would be delta functions of R. And then in some places in the equation of motion, we'll have a square of delta functions. So it's not a well-defined object, and intuitively it's not clear how to deal with this at all. Instead of directly substituting Schwarzschild metric, we decided to take some regularization. And to make things simpler for us, we did a trick, computing instead of simply equations of motion. We just take an integral of these equations of motion with respect to the whole space-time and divide it by infinite. So we do the integral, and take a limit delta t going to infinity, such that we are left with with integral d3x, but it was obtained as a limit of integral d for x over infinitely growing time interval. The point of doing this is that we now can omit total derivatives, assuming that the metric, what we're having in the space-time limit at infinity, that it is just a flat space at r going to infinity, then we can simply forget about total derivatives and the action. Since there are many combinations of derivatives, we can drastically simplify trace of energy momentum tensor equation, and the simplified version of it has a form, very remarkable form, that it can be written through, again, a little bit modified form factors and its derivatives. So it's mass of the black hole-like object. This comes from a normal Ricci scalar term, And this is a contribution from non-local terms, which has a form R box at 1 prime of box R and so on, integrated with respect to R squared in a static metric. It's something computable. Then the task is just to try some regularized static metric, which goes to Schwarzschild and gives back Schwarzschild when the certain limit is taken. We tried several polynomial regularization, but unfortunately, if we act by many derivatives, we get finally some invariants which are divergent, that are going to 0. So it's not a polynomial regularization. It doesn't work for infinite derivative gravity. That's one of our conclusions, and our way out is to use exponential regularization instead, parameterized by alpha and p. P, we will vary this parameter to see whether we have or not regularization dependence of the result. And alpha going to 0 limit exactly reproduces Schwarzschild metric. So we want to see what happens when alpha goes to 0. The advantage of this metric is that all these integrals apparently can be computed one by one exactly. They can be computed analytically. We can study what happens term by term and look at the series which we are obtaining after that. So non-local contributions can be expanded in powers of alpha after integration over the whole space-time. And this is the structure of series which we are usually obtaining in this case. The contributions seem to be unfortunately negative powers of alpha. So when alpha goes to 0, naively we have some infinite contribution to the equation of motion from non-local terms. But we also should, but it's some infinite series which sometimes in principle can be resummed. Moreover, these series are alternating series, and it improves chances for getting some resummation because, for example, if we take this series, each term is divergent when alpha goes to 0, but resummed series lead to exponent of -1 over alpha, which simply goes to 0 when alpha goes to 0. This would be something desired to say that non-local terms don't give a contribution, but this is not something which will be happening automatically because sometimes you cannot do this resummation. You can do this resummation only when the corresponding series in terms of n and in terms of alpha and powers of alpha, when they have infinite convergence radius. This is some clear condition on expansion parameters on series of form factors. This is how I put the link between the form factors and finiteness or infiniteness of contribution to equations of motion on Schwarzschild, on some spacetime which has a Schwarzschild limit when alpha goes to 0. If I'm getting these extra terms to be infinite, then unfortunately I have to conclude that Schwarzschild doesn't go through equations of motion unless mass of the black hole-like object is infinite. So we need infinite amount of matter to be concentrated in some finite volume to reproduce singular Schwarzschild solution in certain cases of non-local gravities. And there is a clear condition when it happens. So the condition is that this it happens when these series are either 0 or finite radius of convergence, which can be computed once given the coefficients beta1n and f1n. So we simply computed exact coefficients beta1n, beta4n, gamma, and so on, all of these coefficients, and get out of them, we get some constraints on how form factors should behave and how it's related to the existence or non-existence of black holes. Yeah, technically we did the computation up to n equal to 11, so up to box to 11 terms. Thanks to computer algebra programs, we were able to perform this and found very interesting things looking at the structure of the series. And one of the things to mention here is that the first term is sensitive only to, is directly correspondent to graviton propagator. And its behavior is crucial for the structure, for having convergence or divergence of the terms. The next term proportional to m cubed here apparently has either better convergence or it has a lower contribution to all these equations of motion. So what we noticed is that what's really important to study is just the first term, which is directly corresponding to graviton propagator. Graviton interactions are not that important for the equation of singularity. These are just some pieces of computation which we got out of Mathematica, like simply to show how the series look like. And the problem is that these coefficients beta in the series are growing very fast. They contain gamma functions, and this leads to the fact that very often these series are simply divergent. We studied certain cases of, we managed just adjusting the asymptotics. We managed to find asymptotics of these coefficients beta. For example, beta for large p, beta coefficients behave proportionally to this multiplication of gamma functions, which contain gamma of 3n over 2 and gamma of 2n plus 1 over p. Then we have sum of beta m, fn, which is here, together with alpha parameter to the proper power. And then if this is growing like gamma of 3n over 2, in order to have convergent series, we need to have beta we need to have fn such that they are falling down with n pretty quickly. Then only in this case, the series can be resummed. So we need some very quick falling down of coefficients fn. And what we want to achieve is that we need convergence of the series in non-zero size circle. Then we can resum series and still have a Schwarzschild limit, like we can conclude that black holes are singular. If we find zero radius of convergence, it means that we don't have singular Schwarzschild black holes. That's the borderline between these two cases. And clearly this borderline depends on how f coefficients depend on n, finally. So these are some plots which we've done to find these asymptotics. And we found that for large p, we have something behaving like gamma function of 3n over 2. For small p, we have somewhat different asymptotics, gamma of 2n, also gamma here. So this one is growing pretty fast. Some plots which we have which show that we adjusted the asymptotics more or less correctly at large n. This series show that m cubed terms are apparently suppressed because they have either the same behavior with n going to infinity or they fall down. So we should not worry too much about interaction terms in this setup. Though it may be not true if there are more Riemann cube terms which are dominating over 3-point interaction coming from quadratic action. So here we somehow assume that the interactions in the theory are kind of suppressed, not that important. And the leading interaction terms comes from kind of non-local Gauss-Bonnet combination, but not from extra Riemann cube terms, which are somehow enhanced by extra form factors. So we don't consider this case because we expect that it will have other problems like growing scattering amplitudes. If we adjust the function, can we have some possible cancellations which affect the asymptotics? For example, we found the sudden cancellation when exactly we have the relation between form factors providing no scalar condition, no scalar degree of freedom. But these cancellations are still not enough, and still we have very fast growing factorial asymptotics of this beta series, of this series. So it will be still very hard to make them convergent and allow for taking allow for black hole solution going through the equations of motion with finite density of matter. What are our conclusions out of this? Convergence, let me also remind some mathematical statements about entire functions with which we are dealing. Convergence radius, according to Cauchy-Hadamard theorem, is simply a limit of, is directly related to series coefficients. So we can simply take our result and find convergence radius in the functions which we are discussing. Then the convergence radius and these properties of the series are also related to maximal growth rate of the function in the complex plane. So maximal growth rate of the function in the complex plane is for entire functions, it can be classified by order and type, where order is defined as maximal of the limit of these logs of the function, and type is defined like limit of maximum modulus log over z to power of order. But this looks complicated, but apparently it's not that complicated. It means that exponential type functions with type s and order rho has a form, has a maximal growth rate as exponent of s z to power rho. And usually in the complex plane, it must have certain growth directions depending on type and order again. If we have such form factors, it's some exponential form non-locality in gravity, which in principle could be. There are also such objects as zero-order entire functions, which are sub-exponential in the growth rate. One of these examples is like sum of exponent of minus n squared zn, z to power n, the function behaving like exponent of log z squared, but of course it's entire because it's just an asymptotics, which is more simply written as an exponent of log squared. For zero-order entire function, we expect that it should be a result propagator in fully local theory because it is sub-exponential and it doesn't. It should satisfy the amplitude should satisfy Martin-Flusser bound, and it should be some nice local theory. But apparently, it looks like it doesn't work for gravity. Though I will also discuss this case in the context of black holes, because we know that in local gravity with log corrections to the propagator, we should have normal black holes. Like Schwarzschild solution should still be there. That's our naive expectation, and I'll show that that's the case. Then we also can have exponential functions of infinite order. They look like exponent of something. Why we are interested in such a mess is that, for example, in infinite derivative gravity, which has a desired behavior in the UV, such that it's power counting renormalizable and ghost-free at the same time. Unfortunately, we don't have a possibility to write form factors in the form of simple exponential type functions. We have to go to exponent of exponential, and a particular form which works is exponent of sigma of k squared, where sigma is given by incomplete gamma function, which compensated by log term such that it's entire. So this function is entire, and the propagator is the exponent of this function. But incomplete gamma function is already exponential type, so the result is exponential of exponential type, and that's the complex plot function in Mathematica, which gives this propagator. But this is just a three-level propagator, and our hope is that it will become a bit more smooth if we consider loop corrections. That's some kind of our expectation at the moment. So let me now summarize our main result, map between having or non-having singularity and form factors of gravity, their order and type. So we found, looking at behavior of series in trace of the equations of motion, we found that in non-perturbative gravity there is a connection between the possibility and the order and type of graviton propagator as UV asymptotics of that maximal growth rate on the complex plane. Some quite non-trivial correspondence. So zero-order entire functions, sub-exponential, their singular solutions are possible. The reason is that if we take a sum of exponent of minus n squared, recall that we have the coefficients beta having these pieces with gamma 3n/2. But once we put here exponent of minus n squared, this will kill all these growth factors. And the series will become with infinite radius of convergence. After that they can be summed to some finite values, or to actually to zero, because they are behaving like they are behaving like series of that type. When entire propagator is growing not that fast, we have still kind of singular solution, possibility for singular solutions. Very roughly speaking, this is something which we expect in perturbatively corrected gravity by loops in the perturbation theory, if it works. So there will be some log corrections which still lead to the full propagator to be sub-exponential. There are other concerns against this scenario, but apparently this is the one which quite expectedly admits singular solutions. Then we have some gap between zero order and order 3/2 functions, where convergence properties depend on regularization, and we are not very certain what's happening. At least this method doesn't show what's happening between this gap, because depending on parameter p, we can have either convergence or divergence of this series. But still, we cannot say that it's a well-defined limit. When alpha is going to zero, is not a well-defined limit in this case, because when limit is well-defined, it doesn't depend on the path along which you are taking this limit. And here there are parameters p and alpha, depending on the path along p. The limit depends on that, which means that there is no smooth limit to singular black hole solution. So it looks like also it's unlikely to have stable black holes with singularity. But there are also exponential functions which grow faster than exponential of z to 3/2. Then we are, regardless of the regularization, no singularity is allowed. So only infinite mass of the hole leads to singular solution, which is certainly not what we call a black hole. It's simply not. We have finite mass of the matter always. So far, I've been discussing some functions which can be expanded in a Taylor series, and I've been relying on that very much. Can it be extended to some entire loop level? Because we know that tree-level propagator should not have any zeros and singularities, but loop-level propagator must have a branch path. So it's a bit different analyticity structure, and full non-perturbative propagator should be a function which is allowed to have a branch cut. But still, the very general analyticity properties allow me to fix the form of this propagator and make some link to the consideration which was already done, and make some conclusions about already now full non-perturbative propagator. What we expect from good theory with regarding its the analyticity properties of the propagator. We know that when momentum squared is positive, it should have a branch cut. It's required from unitarity, or say unitarity with Callan-Lemon representation. There are many ways to derive this fact, but in theories without pathologies, there should be this branch cut and nothing else in the complex plane. No poles and also no zeros, because zeros will bring singularities to the amplitudes. Our problem now is to formulate such a propagator, general form for such a propagator that has only branch cut. Apparently, if it has a branch cut only here, we can make a transformation of this branch cut to infinity at the complex plane, and this map is z equal to log minus k squared, then propagator should be an entire function on the whole complex plane except infinity point, except complex infinity, and this means that it should be an entire function of parameter z. Thus, propagator should be an entire function of logarithm of minus k squared. That's the most general form required by analyticity. This propagator also should have no poles and no zeros, and this can be satisfied only if gamma of z is exponent of some other entire function. This way we can come to one quite complicated form of the general propagator, like exponent of entire function of log, which is looks a bit too complicated. But there is another solution to find the propagator which has no poles and no zeros, and it's an exponent of entire function of k squared to some fractional power gamma. And this is apparently this is some possibility to have not that crazy behavior, but much smoother behavior of graviton propagator after taking into account loop corrections. That's our desired scenario, that three-level propagator of such a crazy form after non-perturbative corrections gets to some much smoother form, which still must have exponential growth along some directions, but not exponential but it's kind of that doesn't have this very complicated structure of essential singularity. But this is an open question so far, and it's kind of part of my ongoing work now. There was a propagator of graviton computed from a density of states for running of densities of states for graviton based on the fixed point in the UV for gravitons, fully numerical work, which was Litin, Pawlowski, and Richard. They computed some propagator which looks at least smooth, and probably there is a correspondence between this starting point and this final point of this propagator. But anyway, if we take the most kind of smooth scenario for UV behavior of the propagator, it must be still growing higher than exponential, and if we are dealing with field theory description of gravity with that kind of non-locality, we don't have singular black holes. So even if it's exponential of z to power 1/4, it's still like singularity is not allowed. Okay, so I'm almost finished now. I'm coming to conclusions. There are many different proposals formulating non-perturbative gravity, but if we are concerned only about graviton two-point function, all of these proposals lead to the same form of effective action. Then one has to specify what is the meaning of form factors of gravity, whether we consider it as a three-level propagator or as a full non-perturbative effective action, where we have already resummed propagators. But anyway, we can deal with even without precise knowledge of the initial, the starting theory. We can simply put a lot of constraints from unitarity and analyticity properties and study general expectations about effective action for gravity in the UV. Of course, if it works. And the interesting link to possibility of having Schwarzschild metric as a solution to infinite derivative equations of motion, the result is that not always Schwarzschild singular black holes can exist. There are, moreover, in gravity with asymptotically safe properties, we expect that form factors should have non-locality of exponential type, because other options that don't work for analyticity reasons, and it's just not possible to put all requirements together, like finite amplitudes plus no poles, no ghosts. Then we are coming to some functions which must be exponential of exponential type to fulfill all these requirements. But these functions lead to the conclusion that we cannot have Schwarzschild black holes as solution for finite mass of compact object. This could be seen in a positive way as a resolution of number of problems related to description of singularity in gravity, simply not having singular solution, but rather having solution with inner and outer horizon. Also with a limit for that there are no too small black holes can also lead to avoiding of many problems which normally appear due to singularities in the center of the black hole and breakdown of gravitational theory. And we formulate the precise criteria for non-perturbative propagator, which relate its maximal growth rate of the complex plane to the existence of singular spherically symmetric solutions. Thank you very much.
Thank you, Anna. I will open with a question, and then if anyone else has a question, you can ask. When you say that all the approaches lead to the same kind of structure of propagator, you mean what you described now? This is somewhat the most general universal formulation for, in a sense, quadratic gravity, right?
Quadratic gravity with form factors, yes. This kind of.
So that you formulate criteria. What would be? I mean, assuming that some modification of GR or whatever the most general gravity theory is, assuming that it is described by the same variables, metric, and we want to somehow have a reasonable non-perturbative propagator.
Yes.
Then the conditions that you are describing are both excluding singularity and also adding some extra good properties in some sense, right? Can you just summarize that part again? I somehow didn't fully follow.
I'm saying that having this section as a non-perturbative description of gravity actually implies, and having also many other nice properties like listed here, imply actually that we cannot have singular solutions, singular black holes. The black hole-like objects will have, we still have to find what are the solutions instead. It's not an easy question, as you can see from the form of the
Yeah. So if you cannot solve generally the theory, how can you make comments about its solutions? I mean, one can try to follow at the technical level what you just said, but the more like abstract, like the bigger logic, I kind of was missing it.
The bigger logic is to try substituting some regularized Schwarzschild solution and check whether the limit of when regularization goes to Schwarzschild, whether this limit makes sense.
There are two questions. One is that, in a sense, this is most general only for the quadratic part, right? Because in principle, there are interactions, and you are assuming that some other interactions will be irrelevant in this context. Right?
Yeah, it looks like so, unless there are some huge coefficients in the interactions, which probably not, in general, is not good to have. It's main to other problems.
And this is regularization independent statement?
The conclusion about functions of form factors of exponential type is certainly regularization independent. There is some range which is regularization dependent, and probably we need to try other regularizations to figure out what's happening. But if the growth rate is very fast, then it's regularization independent. The conclusion doesn't depend on it. So, basically, what we've done, we just took this metric and substituted brute force to this equation. Computed on exact in these integrals. In exact mathematical and studied this series coefficients. Just made a convergence study of this series when they can converge in whether we can take at all the limit alpha to 0, because apparently these are series in 1 over alpha, And limit alpha to 0 makes sense only when the series have infinite radius of convergence. Yeah, then we simply study the criteria for this, like from analysis knowledge about series.
So, if one tries to, again, yeah, there are two different things. One is that trying to find explicit solution for a given system. The other is to try to reconstruct the action for which the theory for which this structure that you write, like with the exponential tracing, is a solution. From what I understand, you didn't try. Well, both of them seems hard, or
yeah, that seems hard, and the point is that we are trying to adjust matter. This E represents some arbitrary matter which we put and which we will produce something. But we show that sometimes we need E to be equal to infinity in order to have this as a solution. Certainly, if we need infinite energy density of matter, it's not a good solution at all. It's doesn't make sense. So in some sense, we don't need to construct what is solution. We just show the absence of solutions, in fact. The absence of solutions with finite mass. Constructing a solution is a different task, which we also try to address, but yeah, maybe next paper.
Would that be correct to say that you make a statement that whatever full quantum gravity theory is, in that theory, black holes are not singular?
If it's a field theory description of gravity, yes.
And this statement?
I think it can be promoted to such a strong statement unless some strong resummations are coming into the game. And so far this is not yet written in a paper. It's like some further studies now and some discussions during this Nardita program too, that it looks like it's not possible to construct a propagator which would be simply exponential type. It needs even if you allow for a branch cut, it looks like it's not possible. At least, or maybe I missed something, but at this moment we think this in field theory description of gravity we need this kind of stuff.
Okay, so is this statement like, was there any precursor similar statement in the literature? Because I'm not really aware, like any statements that in full quantum gravity black holes should not be singular or something. I mean, there are some works I'm familiar to where people construct non-singular black holes in different contexts, including nonlinear electrodynamics and stuff.
Yeah.
But in a strong sense, like for example, trying to do something, some engineering from string theory so that it would be non-singular, whatever I'm familiar with doesn't work. There is still singularity, but none of it was any strong statement in the sense that I'm not familiar with the general conjecture, let's say, if not anything proven, that full quantum gravity should not have singularity.
I think there is not. It's not proven.
Yeah, I would be surprised if it's proven, but as a conjecture or some.
I think it could be put as a conjecture, but here you see we were limited ourselves to study only spherically symmetric metric. Of course, you can one can say that let's do it for more complicated metrics, Kerr and so on.
Yeah, that's harder.
Yeah, that's something which is not yet done. Maybe good check the results. But apparently, the very consideration of full set of analyticity properties of field theory formulation of gravity, I think it's not fully addressed yet. Because people doing asymptotic safety, they don't care about analyticity properties. They do just propagator. They do everything on the real axis. I would say it like this. They don't care about complex plane behavior.
Yeah, I mean, people studying numerical EGR comment that this is as far as I know, well understood fact that Schwarzschild is a very special singular case. Singular not in the sense of singularity, but in the sense that as soon as black hole has some spin, its singularity is not a point but a one-dimensional line. So that there's some sort of one-dimensional cycle singularity that when you go to the limit when spin is 0, just goes to a point. So in a sense, this is a very spherically symmetric solution is a very special one. But cannot say whether any of your conclusions would be modified. My expectation would be that no. I mean,
but probably I can settle myself in a rotating reference frame, rotating with a black hole, and then I should. Well, I mean,
right.
Usually you can obtain the rotating black hole solution from Schwarzschild by just
right, yeah.
transforming, making this kind of coordinate transformation.
Right.
So probably can be done like this. Charged black holes is the next level. It's not of course, it cannot be simply obtained by different reference frame.
Main tool that you are using in the deriving this property is that you use analyticity of the form factors in the complex metric.
Yes.
I mean complex momentum, right?
Yes.
Yeah.
Yeah, I'm kind of although there are some attempts to compute these form factors somehow, but I say that okay, whatever the form factors we have, we require a certain set of analyticity properties for them, and then there are some conclusions which are simply following from that and from some complex analysis theorems. It looks like this analyticity properties allow to make quite generic statements about that.
That's very interesting.